A finite dimensional vector space V with a dimension equal to n is very similar to Rn. For example, any linearly independent subset of V has at most n vectors, and any linearly independent subset of V containing exactly n vectors is a basis. And any generating set for V contains at least n vectors, just like Rn. And any generating set for V containing exactly n vectors is a basis. Let's consider P3. And we know P3 has this basis. So we can say that the dimension of P3 is equal to the number of vectors in the basis, which is equal to 4. If we define the coordinate transformation in this case, it would be from P3 to R4, and the coordinate vector of this polynomial would be the coefficient A0, A1, A2, and A3 right here. And we know phi b is an isomorphism. This also tells us that which two vector spaces are isomorphic. These two vector spaces are isomorphic, right? So P3 and R4 are isomorphic. They have the same structure. How about the dimension of Pn? Here we have a basis for P3, and we know the dimension of P3 is equal to 4. How about the dimension of Pn? That should be n plus 1, isn't it? Another example. Let's consider this set for M2 by 2. We know it's a basis. So we can immediately write down that the dimension of M2 by 2 is also equal to 4. If we define the coordinate transformation using the basis C, then we get a coordinate transformation from M2 by 2 to R4. It maps a matrix ABCD to a vector ABCD. And this phi C is an isomorphism. How about the inverse of phi C? Is it also an isomorphism? It's also an isomorphism. Why? Because we know isomorphisms are invertible linear transformation. And the inverse is also an isomorphism. Let's use phi B and phi C that we defined in the previous two examples to construct a linear transformation that is the composition of phi B inverse and phi C. Is T also an isomorphism? T is also an isomorphism, right? Why? Because it's the composition of two isomorphisms. And the phi C goes from M2 by 2 to R4. So this is M2 by 2 and this is R4. It maps a matrix ABCD to a vector ABCD in R4. And then phi B inverse. Phi B inverse will map. What does phi B inverse do? Phi B map a polynomial from P3 to R4. So phi B inverse will be the other way around. It maps a vector in R4 to P3. So R4 to P3. So the image will be a vector, a polynomial vector. The 5A inverse will map this vector ABCD to a polynomial a plus bx plus cx squared plus dx to the third. And that means in particular, when we look at M2 by 2 and P3, although one has matrices and one has polynomial, they are isomorphic, they have the same structure.